Okay, the record is now on. The useful matrix method is the matrix displacement method. And as you all know, we have done two displacement methods in the past, that is slope deflection and moment distribution. Slope deflection is very useful because you can solve the structure by simply establishing the equations, right? But when the structure becomes very, very large, your number of simultaneous equations also become very large. And you can either use moment distribution method to help solve the problem, but the moment distribution could become problematic as well if your structure is huge. And when the computer was invented some time ago, we have the means to calculate the simultaneous equations in terms of the matrix when we have a large size of it. So this one become very popular, and it forms the backbone of any computer program that you will use. Any computer program is based on the matrix analysis. Okay, and let me tell you that the matrix, if you look at the equation that you use to solve from moment distribution, what you always have is some kind of F equals Kx or Kd, or moment equal to K theta. So on the left side, this is a force. On the right, this is the displacement. Something in between that connects the force with the displacement is what we call the stiffness. That's why I have always emphasized on your ability to recognize the stiffness of the structure that you are dealing with. Okay, so every structural analysis is in this kind of form. If you have the force, if you can describe the structure in terms of the stiffness, you can solve for the displacement, and vice versa. In the slope deflection, when you write the equation MAB or whatever, MIJ is 2EK, right? 2 theta I plus theta J, and then blah, 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 blah. You see, this is the stiffness. You see, that is the force. And then that is the displacement. And when you have a large series of simultaneous equations in equilibrium state, you can always write them in terms of the matrix. And the matrix is something that the computer can recognize. Okay, so, and the most important thing is how the program establishes the stiffness matrix, which will relate the force to the displacement. So computer program nowadays, you know, which one is better than which is judged by which one has the better stiffness matrix to explain, to describe the relationship between the force and the displacement. And this is the secret of all the computer programs, the ETABS, the whatever that you will use in the future. Okay, so we are going to start learning about this from the beginning, say how the matrix could be developed to solve the structure. And because this is just simply the introduction, so we are in this class going to focus on just the matrix displacement analysis for the most simple structure, that is the truss. Okay, so is there any question? This is the big picture of everything. We need this. So we are going to do just the truss. Okay, and now if you don't have any question, we can now switch to this document matrix supplement. Okay, so let's focus on a typical truss member. Okay, now I am going to call this, I have to make it bigger, node 1, 1N, and then node 2. Okay, now at this, 1 minute. Okay, we are going to put the typical orientation. That is a typical XY like this. Okay, so this is the x-axis, this is the y-axis. Okay, and this member naturally should have the length equal to L. All right, and at this dirt one, you could have force apply to it. Okay, and it could also have displacement. So if it's at node 1, you can call it F1 and then D1. And likewise, similarly, at node 2, you could have F, the force, at node 2 and displacement at node 2. So this is nothing, it's just a nomenclature. Okay? So now we can use this relationship of the truss, which is, as I mentioned a few minutes earlier, the most important thing is F equals KD. Okay, so remember the relationship between the force and the displacement in the truss. Hope you can recall that. Okay, you have the displacement, let's say D1 here. It's going to be equal to F1, right? Multiplied by the length divided by AE. So that is the relationship we always have, correct? So that means I can also write the force F1 in terms of displacement. The F1 is going to be equal to AE over L multiplied by D1. See how, let me move this a little bit. Okay, now let me rewrite this. Oops, sorry. So it looks a little bit more beautiful. Seems to be, I was confined by the space. AE over L and D1. Notice that this is F, this is D. So naturally, oh, what is that? This looks like the stiffness a little bit, right? And I can also try to write F2 as well. But you must, I from the midterm exam, I've seen some of your friends still, memorize things to try to solve the problem. Third-year students memorize how to solve problems. That's sad. You don't trust the free body diagram. That looks like a 3. Let me fix that. So right here, in order to have equilibrium, your F2 must be equal to minus F1, right? And therefore, I can rewrite F2 as, I can write F2 as minus AE over L D1. Okay, but this is wrong because from that, I should have drawn this first, but I forgot, sorry. To have that, actually we are looking at the structure with the support, and then that's the F1. My apologies. Okay, and then that becomes your F2 equal to minus F1, and then D2 is equal to 0. Okay, sorry about that. And in similar fashion, I can draw the same structure, but this time the hinge is here, and I apply F2. So I'm going to have D2, right? So in here, my D2 is going to be equal to F2 L over AE. And in similar fashion, I can write F2 in terms of AE over L D2. And again, you should be able to notice the AE over L term, which is the stiffness of a truss member. Let's come back here and try to complete the free body diagram. That means now my F1 must be in this direction and my D1 must be 0. So I can also write that my F1 is equal to minus F2. And therefore my F1 is minus AE over L and then D2, correct? Now we can put this together and form the matrix, right? This can be written in matrix form. Okay, so what's going to be the matrix form? Say that is going to be our equation, correct? So I can write F in terms of matrix. I can write K in terms of matrix, and I can write D in terms of matrix. So let's try to write the F or the force matrix. That should be F1. Oops, it's a small f, right? Sorry. F1 and then F2. And then we're going to have the F1 is equal to AE over L. And then multiply by D1. Okay. And then F2 is also equal to minus AE over L. Multiply by A1. The next one is this one, right? So it's minus AE over L. D2, and then F2 is AE over L, D2. So that becomes a matrix form. I can further simplify this by taking AE over L out of the matrix. Oops, sorry. And this becomes 1, minus 1, minus 1, and 1. And this is too short. D1 and then D2. So without further ado, that is what we call the force matrix, right? That is the displacement matrix. So what is this one?
Stiffness.
Yes, it's a stiffness matrix. The most important thing. Stiffness matrix. Okay. So, we have the form to write the matrix that you can write. It's something like this. F is equal to K D, which essentially is this equation, right? This one. Same, but instead of a typical equation, now it is the equation of the matrix. Now, let me try to complete this. Let me ask you this first. You guys finished this? You need a minute to write down, or tell me?
Finish.
Okay. Just you or everyone?
We finish, Edwin.
Okay. So generally, to make this formal, you actually need to give the way to tell which member in the system you're dealing with. Generally, you can call this member I. Member I. So that means if I am going to write this in full form, I should always have the superscript I everywhere. But I sort of skip writing that because if I write everything in the beginning, it's just too much, too overwhelming. But in fact, when you look at the textbook or anything, the full form is this. It's F1, F2 of, member I. Or, when you write, you member 1, member 2, member 3, 4, 5, 6, 7, 8 of the system. You may write this, you may not. It's just too much. So in fact, this becomes F1 of the member I, F2 of member I, D1, D2 of member I, like that. Okay. So it's simple enough, but it's not enough. Why? Because now we are dealing with only two directions. If you can see, that is, we are just taking a look at the direction of the force and the displacement, which rightly so, because when you look at the truss, you see you cannot have the force in this direction, right? Because the truss is the two force member, it means it can only have the axial force. As long as you have the force perpendicular to the member, you have beam. Okay, but if we are trying to identify something, structure in the real world, you cannot use one dimension to explain the structure. Okay, so you're gonna have to add the y-axis as well. But in doing so, now you know you are dealing with something that doesn't really. Oh, I'm running out of space. Actually, it's okay. I want to write this one. So we need to add this, the displacement in the perpendicular direction to the member. So let's hide this one. Okay. So from the previous one where we have F1 and D1, and we have F2 and D2, we just need to find the way to also identify the force in this direction as well. You will see in the near future why we need to have this. F4D4. But if everything is in the perfect condition like this, we know that F3D3 and F4D4 must be 0, because we cannot have the force perpendicular to the truss member, correct? And neither the displacement. If you have that, it means that you no longer have the pure truss system. So anything related to F3D3, F4D4 must therefore be 0. But now we are going to have the full explanation of the 2D world. So you see this portion, F1, F2, it comes from the development that we have previously, right? This. The yellow portions are the same, but there's these zeros are the ones that we now have to explain the relationship of the force and displacement. When you have force and displacement in the one direction, what's going to be for the 3? So it's going to have to be 0, right? And then likewise for 4, 0. When you have force and displacement in 2, you're not going to have anything in 3 and 4. So that's why the rest is 0 like that. We all know, but now we have the system that can describe the two-dimensional world of the truss. So from this, which we can relate the force to the displacement to form the matrix, we expand this a little bit to include the 2D world. So we have a 2x2 matrix as the stiffness method now. Any question? Pretty easy, right? Crystal clear?
Yes, yes.
Yeah, maybe. Okay. This method is very simple. So those of you who decide to remain in the class will be sorry if you missed this. Okay, so those of you who are here, congratulations. You see that it's very, very simple. Now, this is the development I find very easy to understand. So I start off with this, but take a look at the nomenclature. This is 1 and then 2. 1 is in this node, 2 is in the opposite node, and then come back to 3 and come back to 4. Most of the textbooks you will see will not use this nomenclature. Generally, they would use this as F1, D1. This becomes F2, D2. This becomes F3, D3. Then that becomes F4, D4. So when I switch order, it means that we have the relationship with 1 and 3, right? And 2 and 4 is just nothing. So the order of the matrix will switch a little bit and it becomes like this. You see, that's 1, 1, and then 1 and 3. 3 and 1, 3 and 3. You get the picture, right? Okay, so this is more common. But, you know, I think one of two things that I'd like to mention here is, first of all, the order is not important as long as you understand the relationship between the force and the displacement. You can write your metrics any way you like. Second is that some students don't seem to like to follow this very much. So they create their own, say, sign conventions and nomenclature and everything, but without proper understanding. So they mess up. Okay. Now, if it was for someone like my very own advisor, he likes to switch everything around to, oops, sorry. He likes to switch everything around to mess with students' head because he emphasized everything on understanding. So you don't have to follow the form all the time to write, okay, everything must be written like this. But in another class, I remember having another professor from Germany. So you know how the Germans are like, everything must be in order. So, you know, the metrics must be written like this. And he had the class before my advisor, and then my advisor would come in after his class and, oh, you have that still? I'm just going to change this and then blah, 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 blah. And just, you know, in the end, you must understand that if you use this kind of thing, you see, F1 and F3 are related because they're in the same system, and 2 and 4 must be 0 if it's a truss. So you just switch this around, no big deal. But in the real world, I think this is more common because generally this is going to be your node number 1. This is going to be your node number 2. So maybe it's much more convenient for the computer program to identify, you know, node number 1 first and then node number 2. And if you have the burning question in your mind, which one is 1 and which one is 2, it doesn't matter. It depends on how you define your structure, really. You could call this 1, you can call this 2. So the order is just going to be swapped, that's all. But in the end, this is the typical form of your matrix for the truss, okay? The force matrix, the displacement matrix, and the most important thing, the stiffness matrix. So insofar, any question? Okay. Any question, folks? No question? Now, insofar up to this point, what we have done is we have established the matrix for the member. Okay? But just one member. That's why we're saying that we have established the system that is the local system, because it's just for one member. Now imagine that when you have a truss system, of course a truss must have more than one member, correct? If you have only one member, you wouldn't call it a truss. So let's say in a truss system, one member is in this direction, another is in this direction, another is in that direction. How could you use just one coordinate system to handle these 3 members, which they, you know, they line in different directions? What we have now is just the system for one member. Okay, it works when you have the coordinate that lies. Let's say if you look at this member, which looks like that one, you have the D1, D2, D3, D4 in the perfect direction like this. But when you look at this member, what's going to happen? So the system up until this point is what we call the local system, because it could handle just one member in its own axis. Because when you look at this member, Now, if you are going to use this local node, it's going to be the, this local system. It's going to be the force and displacement in this direction, correct? Parallel and perpendicular to its own axis. So that this is going to be the F1, F2 of this member. And you look at this member. This is going to be the F1. And then this is going to be the F2. So each has its own F1, F2 in the local fashion. So that means this alone is not enough for us to solve the problem of the entire structure. That looks like this. In order to form the matrix for the entire structure, we need another important knowledge so that we could, bring them all together as one structure, not just one individual member. Okay. For that, we need the system. What's the name? The system that can help us transform this into what we call the XY system of the entire structure. Okay, you now can see that you have this member where its system is F1, F2 in its own local axis. But this is not going to work because this is the axis of the entire truss. So we need to find a way to bring this system into the system of the whole structure. And this too must be brought into this. So the system for one member, we call it local. We need to bring this into the system of the entire structure. That is what we call the global system. Okay. So from this on, I am going to twist the member a little bit. So let's say now we have the member lying in any direction like that. Okay. So let's say for this member, you see this black one, this is going to be the coordinate system of the global, right? And the red and the blue, that will be the local coordinate system. Okay. The black one, they are global. We need to find a way to bring the local coordinate system into the global ones. Are you still with me?
Yeah, yes.
Good. So, okay. Now from this, we can identify the orientation by, of course, the trigonometry. So this will give us the orientation of the member comparing to the global coordinate system of the structure. Okay, so let's call this. Let me check with this. Okay, so the blue one, you know what? Let's use a different color for this. Let's use the that will do. Okay, so now in the local, you see, the local ones are the one parallel and perpendicular to the member. So let's say this is D1. So that's going to be D3, right? And let's say this is going to be D2, and that's going to be D4. Okay. And in the global one, okay, let me use black so that the colors are the same as this. This is going to be D1, the capital D1, so that you know it's in global. That's D2. That's D3, and then that's D4. Okay. I have the end results here, but I should not. So let me try to find a space for this. Okay. So when you have this, now let me try to write down. The one here, I'm out of colors. This remind me of the way some of your friends use so many colors in both the exam and the homework, and I run out of colors to grade. Very funny. Anyway, so this D1, you know, if that's the angle, if this is theta, if this is theta, that is theta, correct? So now I hope that you can see it's going to be the D1 here. Yeah, let's see if I can squeeze it. This D1 is going to be equal to the capital D1 in global cosine theta. D1 cosine plus D2 sine theta. Right? You with me? Are you? Hello?
Yes.
Okay. And D2 here is going to be equal to minus D1, right? Because it's going down, minus D1 sine theta plus D2 cosine theta. And in similar fashion, D3, maybe I can have more space by moving this up. Okay. D3 in similar fashion is going to be equal to D, capital D3 cosine theta, correct? And plus D4 sine theta, and then the D4. Oops, running out of this space now. It's going to be minus D3 sine theta plus D4 cosine theta. Can you see this? And from this, I can again write this in the matrix form, which leads to the one that you see below. Okay. Now you can see that, you know, this one is coming on top of that a little bit. So let me move this out of the way. Okay. So now you see only D1 and D2 and capital D1 and D2 are related. So that's why now you have the matrix that, you know, has 0 here and here for the submatrix. Okay. You can see the form now, right? This is the matrix that relates the local coordinate system to the global coordinate system. So it is called the transformation matrix. That is the transformation matrix. Okay, it transforms the local value into the global and vice versa. And the same can be said if it is the force. So I can do the same for the force. Okay. Now we are heading to the break. This transformation matrix has a very important property. Sometimes they call it T, transformation matrix. Some call it lambda, but I'm familiar with lambda, so I'm just going to call it lambda. Okay. The most important thing for lambda is that the lambda inverse is exactly the same as lambda transpose. You know what transpose is?
Yes, yes.
Just you? What about the rest?
Can't remember.
Good. It's good that you tell me. If you're afraid to say, nobody's gonna tell you what it is, right? But now I know you don't know. I can just show to you very easily, but it requires another color. So let's say I have a matrix like this. This is the diagonal axis, right? When you want to transpose the matrix, I mean, you swap the members by this axis. Okay. Let's say my matrix is this 2, 3, 4, 5. I transpose it. What am I going to have? My axis is going to be this one, right? So 2, 5 remain the same. I swap 3 and 4. That's transposed. Like this. And you see my hand transposing like a rapper. Can you see that?
Yes.
Okay, so that's transposed. So that means if you want the inverse matrix of this, because the most important thing of the inverse is that when you multiply the matrix with the inverse, what you're gonna get? You're gonna get the matrix that looks like this, right? It's all gone. It's just one in terms of simple mathematics. Okay, so it's very important. If you want to calculate the inverse of this matrix, you're going to have to find the determinant and whatever that is. Remember that? But now you want to find the inverse matrix of this transformation matrix. All you have to do is transverse this, and then you get it. So can you write the inverse matrix of this one? You just swap the sign term, right? Okay, so now, because I have this right after that, we're gonna do something similar to this, but you need to know why. So I'm just gonna find a space down here, okay? We're gonna come back to this, but let's forget about that first. I'm gonna use this space to try to explain why. And I think it's only 4 minutes before the break. So I don't know if I should do this or I should have the break first. What do you think? Hello?
Can we continue?
Pardon me?
Can
Can you what?
we continue?
You want to continue?
What about others? I'm okay for both.
Yes, we can.
Okay, just it's a very faint voice. Okay, yeah, we can continue. All right, let's continue. If this break is long, another break. I mean, if this session is long, another session will be shorter. That's all. You know, in the end, you're just gonna have the same amount of time. So, okay. Before we go to that, let's rewrite this. Okay. From this, you know, the normal, say the lowercase letter. The normal letter is the local axis. The capital one or the uppercase is the global. So from that, I can write this. Let's be consistent with symbol. Okay. You multiply this transformation matrix with the global coordinate system, you're going to get the local values. Similarly with the force. Okay. So from this, Okay. Hang on. Okay. And from this, f of the local system is equal to the transformation matrix multiplied by the matrix of the global system. Okay. Remember that f is equal to KD. K now should be small k because we are looking at the local system. Okay. Excuse me, it has to be for this one. Sort of a bracket, okay, and D. But from F equal to KD, I am going to replace this D with this. So, okay, this is going to become K of the local multiplied by lambda and then displacement of the global. Okay, now it is equal to lambda F. Just bring this down. Okay. Now what do I do? I want the everything, because we have developed things in local, right? So we now want to the explanation in global. So what do? I am going to get rid of the transformation matrix by multiplying with its inverse. So now I have the inverse of this local, I'm sorry, the inverse of this transformation matrix multiply with K of the local and then lambda and then B. On the right side, I now have put the inverse of the transformation matrix against its own. So with doing that means I now have eliminated this, correct? So from this, you can see F, you can see D, and you see K in this form. So I can rewrite this, you know, left to right, right to left. Now I have the global system as the force matrix is equal to the inverse of the transformation matrix multiplied by the local stiffness matrix and then the transformation matrix and then displacement in global. So meaning now I can move every information I have in the local coordinate system into the global one. And I can change the local stiffness matrix into the global one in the global direction by having this. I can multiply the local stiffness matrix by the inverse of the transformation matrix and the transformation matrix itself. Okay, which is what we have here. This, excuse me. Notice this first before I write a lot of things on it. You see, this is transformation matrix. The minus sign is here, sign is there. When I do the inverse, you see how things got swapped. Oh, but that's wrong. I forgot to change that. Yeah, it's supposed to be, I'm sorry, it's just a copy and paste error. So this has to be like this. You know, after all the talk, this is wrong. Okay, it has to be like that. Okay. So that's the transformation matrix or the inverse. Okay. Of the transformation matrix, okay, the transpose of the transformation matrix, and then this transformation matrix itself. This is the local stiffness matrix. You multiply everything Do some calculation music, and this is what you have, folks. This is the stiffness matrix in the global direction, or you can just call it maybe with a different color, global stiffness matrix. Okay, so only 5 minutes late. So this is the global stiffness matrix. Now you can write the matrix of any member which lies in any direction in terms of global system by using this matrix that you see. So it doesn't matter now whether your member is in the typical direction, it's inclined like this, or it's perpendicular to the normal XY in the global. As long as you can identify the orientation in terms of, you know, the theta, you can now write the stiffness matrix of each member in global direction, by using this. But keep in mind that this matrix is based on this coordinate system, 1, 2, 3, and 4. Okay, so is there any question? And I never test anyone's memory. You know, I always give this in the exam, so you don't have to memorize it. As long as you understand how you can identify this, you know, this is a piece of cake. And remember that this method was developed for the computer usage in mind. Computer is not as smart as a human being. The only, you know, say you guys like to play, you know, the strong point, weak point, that kind of thing on Facebook, right? So computer program, strong point, doesn't make mistakes. Weak point, stupid. Okay, human being, strong point, smart, weak point, make mistakes all the time. So, you know, this is developed for computer in mind. So computer cannot decide for itself. It just has to follow path. And, you know, so this one method should be simple enough for the computer to follow. Okay. Any question? Now we have this, we can take a break.
That means if we finalize, we're gonna use this form to calculate, right? For K.
Well, you're quite ahead of our time. So I'm gonna give the answer that you deserve. You use this. You know, it's I have a habit of pointing at the iPad, and then I recognize that you don't see me. Here, you're going to use this if you're solving problem in global system. But say, when you want to solve the forces acting on your members, the force you want for your members will be the force in the local direction, correct? Like this?
Yes, yes.
So you're going to have to use the this if you want to solve anything locally. It depends on where you are. If you want to solve the entire system, you need a global system, because you cannot assemble the matrix for the structure if you use the local system for each member and you try to bring them together. They don't talk to each other if they speak their own local language, correct?
Yes, yes, I see.
They need the global language that they can communicate for the entire system. So we're going to use this global stiffness matrix if we are going to solve something globally. And then if you want to solve something locally, you're going to have to use the local system. It's a very important question, actually. And I hardly explain about this until the very end of the example, hoping that students will get the point, but they actually don't. So yeah, it's good that you asked first. And I was thinking about that subconsciously, actually, and then you asked for it. Good. So now we have the two systems. Always, the global system for the entire structure, and the local system for each and every individual member. So if you are going to solve the structure, it means you are going to solve the entire system, correct? We need the global system. And then when you want to focus your analysis on one member, you need the local system because it becomes local now.
That means it depends on the purpose of calculation, right?
Yes, correct. Any more questions? But before we get to that, we now have the global stiffness matrix for one member. It's not for the structure just yet. So we need one huge important step to put the stiffness matrix of each member to form the stiffness matrix for the entire structure. Okay. Any question? Oh man, you know what? It was a good sign that it rained this morning, but now it's just full-blown sunlight again. So if there isn't any question, I'm going to stop the recording.